sorry, the video get blocked in between. So welcome back once again, study with Adu here. Let us start. Please subscribe, like and comment, etc, etc, everything. No time to waste. So we were telling about Zaitsev rule. So that's about Zaitsev rule, elimination reaction. In NCERT only Zaitsev rule is given, so let us only go with Zaitsev rule. Now after this elimination reaction over, next type of reaction is reaction with metal. Here reaction with metal, here we have our special reaction, that is Wood's reaction. Wood's reaction. What is the reaction? Yeah, you are having Rx and sodium. Rx and sodium. 2 Rx and 2 sodium. What happen here is what we get is we get RR. Here the product formation can be drawn and shown. Drawn and shown means like we are having Rx one second. Yeah, we are having Rx plus Na 2Na plus Rx. This Na will go and join with this X. This Na will go and join with this X. This will be like minus. It will be like radical. So these two radicals met, they form a bond, and hence we get RR plus 2NaX. This is the product form. Okay. Reaction with the metals. Now next, the second reaction is what? Formation of Grignard reagent. Very simple. Take a RX compound. RX compound. Into that I am adding magnesium. In dry ether medium we get our favorite organometallic compound. What is it? RMGX. This is called Grignard reagent. Okay. Yes. And next thing is that specialty here is that there is one more thing told here. If we take this Grignard reagent and if we react it with water, what happens? It reacts vigorously or explosively with water, and we get the corresponding hydrocarbon and MgOHX. This is a very important reaction. Questions have been asked on this. Okay, questions have been asked on this. Learn it, not by heart it. Learn it, understand it. Okay. Yes. RMGS plus H2O gives RH plus MgOH. This is the reason why dry medium is preferred for preparation of Grignard reagent. Preparation of Grignard's reagent. Dry medium. Okay. Yes. By this it is coming to an end. Now now chemical reactions of haloarene. Now till now we were doing about haloalkene. Now chemical reaction of haloarene. Now I think some helicopter is going outside my house. I don't know what it's called. Yes, helicopter is going. Yes. So first one is will haloarene undergo nucleophilic reaction? So question, will haloarene undergo nucleophilic reaction? The probability of nucleophilic reaction in haloarene is very less. The reason is resonance effect. Once again, we will draw that resonance structure because that is important for board exam also. That is, this is the structure of Cl. Cl is having its lone pair, 3 lone pair. What happens? One lone pair fall here and this will go here. So we get a partial double bond character for this bond. Now the normal resonance structure is in a textbook or you can draw it yourself. Here there is a partial double bond character, right? So when there is partial double bond character, the bond is more strong, and hence substitution is difficult. But still OH group will be substituted in a very high temperature, that is 623 Kelvin or something like that. OH group will be substituted. And another reason for its inability of substitution reaction is that, look, if we are undergoing a SN1 reaction, you think SN1 reaction, carbocation should be formed. Here the carbocation is this one. You have learned in the reaction mechanism that most unstable carbocation is this thing. Which one? Unstable carbocation is this thing, phenyl carbocation, because this destroys the aromaticity of the compound, okay, and the resonance is depleted, or the resonance is disturbed, so this is not preferred. Now there is one nucleophilic substitution reaction that we should learn, that is with NaOH. This is our Rx. Into this we are adding NaOH 623 Kelvin and 300 atm pressure, extreme conditions, and H plus hydrolyzing it. What happens? Then we will get OH. Then we will get OH. But we are having Cl here and an NO2 group in the para position. The reaction can be made simple, that is NaOH can be somewhat easily added in 443 Kelvin, and H plus. Some pressure and all not needed. Somewhat more easily we can do the nucleophilic substitution reaction. The reason is that this NO group have a special mechanism. You just learn it that when NO2 group is coming, there is a extra resonance structures that's coming for this compound. Hence NO2 make the compound nucleophilic substitution more easy. Or this you can understand that when NO2 come, the partial double bond character is disturbed. The partial double bond character is pulled towards NO2. So partial double bond character strength will decrease it. So what happened here is that we get OH plus NO2. Okay. Yes. Now if you are having two NO2 groups, that is two NO2, one at ortho position, one at para position, then the specialty is that very less, some more less temperature only needed, that is only 368 Kelvin is needed. 368 Kelvin means less than some degrees less than the boiling temperature of water, right? So only that temperature is needed. It will be more easy, that is we will get the compound as this thing. Okay, now if you are having the NO2 group at both the ortho position and the para position, that is this compound, then we just like little warm water itself can initiate the reaction, that is NaOH and just warm water means 50 degree water and all can initiate the reaction. 50 to 30 degree water, just warm water. We get what? We get OH and 2,4,6 trinitrophenol. We get 2,4,6 trinitrophenol, this compound. After this in NCERT, why does NO2 decreases the double bond character? The resonance structures are drawn. Please refer it. No time to explain. Please refer it. Now we told that only haloarine will only show some electrophilic substitution, nucleophilic substitution reaction due to its double bond character. But haloarines mostly show which? Electrophilic reactions. Electrophilic substitution reactions. How does it show? Look, first thing is that we are having our haloalkene, that is haloarine, that is this thing. Now thing is that there is a double bond forming here, this is going here minus. Here if we look that in the resonance structures, there are negative charges in the ortho, meta and para position respectively. Negative charge due to resonance in ortho, meta, para. So really this chlorine is a ortho para directing group although it is what, deactivating due to minus I effect. It is a deactivating group. Usually deactivating groups are metadirectic, but chlorine, this haloarenes are ortho-paradirect in deactivating group. They are very special. Now there is negative charge due to resonance. So due to this negative charge, electrophiles can come and join in this ortho and para position. So we are having the electrophilic substitution reaction, that is we are having this compound plus Cl2 AlCl3 anhydrous AlCl3 or FeCl3 for your preference. We get this or para position or ortho position. Para position is more what preferred because of less steric hindrance. Because this is minor, major, because here there is less steric hindrance. One is here and one is here, but here it is very near to each other, so there is more steric hindrance. Okay, yes. Now 2, nitration. There is an addition of NO2. This is the same as what you learned in hydrocarbon, that is chlorine, HNO3 and HNO concentrated H2SO4. Here HNO3 acts as a base. This is very important. This question has been asked. In a nitration reaction, what is the base? Here concentrated H2SO4 is more strong acid than HNO3. Therefore concentrated H2SO4 acts as acid and HNO3 acts as a base. Very important question. Okay, now we are having this compound, that is ClNO2 plus ClNO2. Here also para is major, the other ortho is minor. Now third one is sulfonation. That is we are having this thing and add concentrated H2SO4 and heat it. So we get SO3H at the ortho and one second. We get SO3H at ortho and para. Here also para is the major and ortho is the minor product. Okay, one second, sorry. Okay, this here. Now next one is what very important reaction, that is Friedel-Crafts reaction. Friedel-Crafts reaction is you have learned in hydrocarbon 2, that is alkylation. First one is alkylation. What happens? Yes, we are having the benzene ring, haloarene plus CH3ClO, CH3CH2ClO, any other haloalkene. Anhydrous AlCl3 is used here, very important. We get chlorine CH3 or at para position. Here also para is the major and the other one is minor. Ortho is minor, not NO2. It was a CH3. Okay. Now next one is acylation is also there. So not only alkylation but also acylation is there. Friedel-Crafts acylation. That is this compound and is CH3 C double bond O Cl. Here also anhydrous AlC. Here we are using what? Acid anhydride, acid chloride. Acid chloride. Okay, anhydrous AlCl3. Here we get what? Acetophenone. Not normal acetophenone, 2-chloroacetophenone. Here also we get, here the other place also we get. But here also what? Para is the major and ortho is the minor because of steric factors. Okay, noted. So this is about haloalkane haloarenes chapter. Okay, not we are having some more reaction. This is about electrophilic substitution reaction, not haloalkane haloarene. Next one is reaction with metals. As Wood's reaction and other reaction, we are having some reaction with metals in haloarenes too. First one is Wood's fitting reaction. Wood's fitting reaction. Wood's, not WRTZ. Wood's fitting reaction. Fitting reaction. 2 T's. Fitting reaction. That is same as the Wood's reaction. So instead of haloalkane, we are using haloarene only. Is the difference. Take 2 haloarenes plus 2 Na. Then what happens? Sorry, not 2. Take 1 haloarene, 2 Na, and 1 Rx. Any haloalkane. Here what happened? We get this compound, that is like a alkylation reaction. Alkylation happens and we get 2 NaX. This is the reaction. Just rearrange it accordingly. This is Wood fitting. Now another reactions there, that is just fitting. Just fitting reaction. Fitting reaction. This one we use 2 haloarenes and 2 Na in dry acetone. Usually Wood's reaction is in dry acetone medium. Sorry, dry, not acetone, dry ether medium. Here also there was dry ether medium. I forgot dry. It's in dry ether medium. Dry ether medium. Okay. We get here is what? We get, I'll draw neatly. This is like something. Yeah. We get biphenyl as the product. Biphenyl and NX. Okay. By this reaction come to an end with the reaction with metals. Now some reaction from polyhalogen compounds. Polyhalogen compounds, that is oxidation of chloroform. One reaction is oxidation of chloroform, that is formation of poisonous gas phosgene, that is 2CHCl3 plus O2 in presence of sunlight we get COCl2 plus HCl. This thing is called what? Phosgene, a poisonous gas. Phosgene, a poisonous gas. Okay. Now another important structure from polyhalogen compound, important structure, that is structure of DDT. That is para-para-dichlorodiphényl. Para-para-dichlorodiphényl trichloroethane. The structure will be dichloro-diphenyl, para-para-dichloro-diphenyl trichloroethene. This is the structure of DDT. This structure is important. They can ask how many chlorine is there, how many that is there, how many this is there. So just learn the number of chlorine also. How many chlorine is there? There are 1, 2, 3, 4, 5 chlorine, 2 carbon, 5 chlorine and 2 phenyl ring. 2 phenyl ring. Full form also important. Para-para-dichloro-diphenyl trichloroethane. Okay. So this is about the chapter haloalkanes and haloarenes. Now we are going to the next chapter, that is alcohols and phenols. This is also important. This chapter is also very important. Just taking some time for you to rest. 1 minute. Okay. Over. First one is alcohol and phenol. Alcohol, phenols and ethers is also there. Like what Williamson synthesis and all ethers. Okay. One, that is not one. First thing in this is preparation of alcohols. The first method is acid catalyzed hydration. Acid catalyzed hydration follows which rule? Markovnikov rule. Markovnikov's rule. It's a rule. Markovnikov's rule. Okay. And the reaction is like there is also what mechanism given. No need of mechanism now because we are at the last phase. No time for mechanism study and all. So just to a double bonded alkene, we are adding water in presence of an acid. So acid catalyzed hydration. What happened? We get alcohol as the product. Here Markovnikov rule is formed. Markovnikov rule is preferred. That is, look, what is Markovnikov rule? CH3, CH2, CH2, double bond, not CH2, CH double bond, CH2. This is a compound, you think. Now if you are adding, I am adding water in presence of H plus. Here what happened? There's a confusion. This should go here and OH should be coming here, or this should go here and OH should be coming here. What happens? According to Markovnikov rule, OH should be attached to the carbon with a more number of substituent group, or it's very simple, attached to the carbon. I am just telling you a trick. Attached to the carbon with a lesser number of hydrogen. So here in this 2 carbon, here there is 2 hydrogen, here there is only 1 hydrogen. So attached to the carbon that is having 1 hydrogen. Over. We get CH3 here, and we get the compound as butan 2 all. Not all. Okay. Butan 2 all. Okay. This is the basics of acid catalyzed hydration. Next one is the straight opposite of what acid catalyzed hydration is telling about. That is by hydroboration oxidation. Hydroboration oxidation. What should we do here? That is if you are having a compound CH3 CH double bond CH2, into this if you are adding what BH3 twice, that is, this is called diborane. BH3 twice, what happened? We get 3 anti-Markovnikov alcohol as the product. This 3 anti-Markovnikov alcohol as the product. The thing here is, the addition is opposite to that of acid catalyzed hydration or anti-Markovnikov's addition. Look, which one is preferred? Acid catalyzed hydration or hydroboration? Here there is 3 yield, like more number of yield is there in hydroboration oxidation compared to acid catalyzed hydration. Therefore, this will give us more product or more yield. Okay, more product or yield. Hydroboration oxidation give us more yield. Now hydroboration oxidation is over. Now what we are going to do is that we are going to prepare alcohol from reduction of aldehydes and ketones. Look, Aldehydes and ketones are formed by oxidation of alcohol, that is using PCC, CrO3, John's reagent, etc., etc., etc. So if you reduce if you reduce aldehydes and ketones we should get alcohol. That is RCHO plus H2 in presence of palladium. This is called what? Reduction. Addition of hydrogen is called reduction. We get ROH. We get ROH? No. We get RCH2OH. There is no difference in carbon atom and all. This is not Gabriel Thallimide synthesis or what Hoffman bromide degradation and all. So we get the corresponding alcohol. If we are using a ketone, H2PD, we will be using NaBH4, that is sodium something like that, sodium boron hydride. Okay, NaBH4, I learned it as NaBH4. That's simple. We get RCOH HR dash. This as the compound. Okay, this is from reduction of aldehyde and ketone. Now if we need, you can reduce carboxylic acid directly to alcohol. So reduction of carboxylic acid also a method of preparation of alcohol. Reduction of acid, just writing acid, that is RCOH. You can reduce it directly using a expensive reagent, that is LiLH4. It is expensive because aluminum and all is there. Then hydrolyze it, we get this thing. This is a very simple method, that is just to put it, we get it, very fast reaction too. But LiLH4 is expensive, so we will use another method, or what we do is that we convert this RCOH to ester, and we get RCOOR dash, fruity smelling substance, and into this ester hydrogen and catalyst, or H2 and palladium, platinum, nickel, anything is added, and ester is reduced to RCH2OH, two alcohols, RCH2OH plus R dash OH. Okay, yes, this is the method. Now next one is from Grignard reagent. This reaction is there to study in aldehyde ketone 2, that is nucleophilic substitution of aldehydes. So this reaction is really from Grignard reagent, means this reaction is also from which one? Aldehyde ketones 2. So we are taking a carbonyl compound and we are adding RMgX into it. Here what happens is that this oxygen will pull its one bond, and this R go and attach to the C. So we get an adduct. This C double bond of R O minus MgX plus. This thing is very important. This is called a adduct. This is an intermediate. Now we are hydrolyzing it. We get CrOH plus MgOHX. Okay, yes. Finally we got it. So you can use different aldehyde and ketone to prepare different alcohols. So this is a reaction. This is also a nucleophilic substitution reaction of which one? Aldehyde. No, nucleophilic addition reaction of alcohol. Of aldehyde and ketone. Okay. Now these are the preparation methods for alcohols. Now let us do some preparation methods for preparation of phenols. Phenol can be prepared by which method, from different methods. The first method is from haloarine. This reaction is called as the nucleophilic substitution reaction of haloarine. We learned few minutes ago, the 623 623 Kelvin, 1 second, 623 Kelvin and 300 atm high pressure. What? Nucleophilic substitution reaction only takes place in this case. I told you we get O minus Na plus is like an intermediate. Now into this, when we add HCl, we finally get our desired product, that is phenol. So this is the first method. Now next method is, I'll take a break and come. Okay, sorry, I took a break and came back. So first we told from haloarine, that is nucleophilic substitution reaction. Now second method for preparing phenol is from benzene sulfonic acid. Sulfonic acid. First of all, take benzene and add oleum, H2S2O7. Oleum means H2S2O7, H2S2O7 or oleum. What happens that we get sulfonated benzene, that is SO3H. Now into this you can add NaOH and water, so that we get phenol. This is the next method. Third method is very important method. This method exists in 2 chapters, that is from diazonium salt. That is you know that preparation of diazonium salt, I'll just write once again, that is NaNO2 plus HCl in 0 to 2, that is 273 to 278 Kelvin, 228 to 278 Kelvin, we get what? Diazonium salt, that is N2H plus, N2 plus X minus. Into this, just add some water, warm water preferably. What we get is phenol, OH plus N2 plus HCl. Okay, now this is the next method. It's the most important too. Now next one is from cumene. Cumene is, this compound is called cumene. 1 second. CH3, this is called cumene. Into this add carbon, into this add oxygen, so we get this intermediate is very important. Learn this intermediate. That is COOH, CH3. Into this add acid and water, we get OH plus CH3, C double bond or CH3, aldehyde and acid. This thing is important. When we should add oxygen, then we should add water or H plus and water, that is acid catalyzed water. Okay, so what happened? We get acetone and phenol. Okay, yes. Now I am going to do one question. Try to answer it. This is the question. NaBHF4. Please answer it. Here what happens? Yes, just the ketone group converts to alcohol. No other groups have no effect when NaBH4 is added. It is normally OCH3. Okay. Yes. Okay. Yes. Now should we do one more question or should we skip it? No need, it's what similar type itself. I will do this thing you can do. CH3, CH double bond, CH2, H2O, H plus. This is what acid catalyst. So Markovnikov rule. This is COH, H, CH2. This is the product. This is the product, Markovnikov. If it was BH3 twice or B2H6, what should have been the product? Should have been CH3, CH2, CH2OH. Okay, this is the difference. This is the difference between both. Okay, yes. Now preparation over. Now we will be going on to chemical reaction. Chemical reactions. That is, first one is related with the OH bond cleavage. That is O and H bond cleavage. First OH bond cleavage. First, what should come to your mind? Yes. First one is acidity. Acid character. You can just check if you react ROH with Na. We get 2RONA, sodium alkoxide and hydrogen. This is like a acid base reaction. This is like an acid base reaction. Okay. This compound is called sodium alkoxide. If it was phenol also, we'll get something like this. I'll take phenol, add 2 Na, 2 phenol, 2 Na. We get 2 ONA, that is sodium phenoxide plus H2. So this is showing us the acidity of alcohol and phenol. That is, this is what we did now is reaction with metals. Reaction with metals. These are examples for reaction with metals. Okay, perfect. Now this acid character. If there is a plus I effect group near the CH2OH, what happens? We'll just explain. You know that. You just consider secondary, that is 2R groups, secondary alcohol and tertiary alcohol. This difference, if you understand, everything is in your hand. You know the difference, nothing to understand and all. COH, you know that. Acid character means release the H plus, so O should be more electronegative. If an alkyl group is there, it is plus I effect, so this oxygen will become what? This negative charge will reduce. There are 2 groups, more plus I effect, very less. There are 3 groups, very much plus I effect. Oxygen is least electronegative, right? So the order for which one? The order for alcohol character is primary alcohol is more acidic, secondary alcohol, tertiary alcohol is least acidic. And this is alcohol and this is water, which is more acidic. Here instead of an R group we are having an H. Here we have R group, so plus I effect, plus I effect is there, plus I effect. So this is less acidic. Here there is no plus I effect, the just hydrogen. What hydrogen is like deaf and dumb people, doesn't do anything, just simply stand. So this is normally electronegative. So here acid strength is orders this thing. What? Alcohol is less acidic than water. But if you are considering phenol should be less acidic. You know that water is more acidic than alcohol. But really phenol is more acidic than water. Why? It is due to resonance. Look, this double bond fall here, this come here, minus charge. Here a partial double bond is there. Partial double bond. This lead to the oxygen to be more electronegative. If more electronegative, that means what? More acidic. That is the reason why. This due to this resonance and more electronegativity, phenol is more acidic compared to water. So I have to ask you something. Consider these two alcohols. Now these two enough. This two alcohol, which will be more acidic? Yes, this will be more acidic. Why? This chlorine is a electro withdrawing group. So this chlorine will pull the electrons from R. So the plus sign effect strength towards this oxygen will reduce. That leads to this oxygen becoming more electronegative. Okay. So this leads to what? More acidic character. Therefore RClCH2OH is more acidic than RCH2OH. So acidicity of RCH2OH, water and phenol is this thing. So if an electro withdrawing group comes somewhere, acidity increase. So I have to ask you something. We are having phenol and nitrophenol or nitrophenol. Which one is more acidic? Yeah, this one is more acidic. Nitrophenol, electro withdrawing, minus I effect. So more electron is withdrawn. So more electronegative. The more electronegative. So this hydrogen is more electropositive. Therefore what? More acidic. So acidic character is orders like this. So this is very important. Very important. This is the only important part in this chapter. Okay. So this is about acidic character. Now the next reaction is esterification. I'll just come now after a 5 minutes break. Yes. So next reaction is esterification. This reaction is very common. One of the most important laboratory confirmatory tests for carboxylic acid. For your practical exam also, this test you may be doing in the lab. I don't know if you will be doing. You may be doing. Alcohol phenol react with carboxylic acid, acid chloride, acid anhydride, etc. or most of the acid derivative to form ester. That is ROH plus RCOOH, R dash COOH, anything. In acid catalyzed. The reaction is acid catalyzed, don't forget. We get RCOOR dash. Plus H2O. Fine. You know this reaction itself we have written somewhere before. One second, let me check. Where did we write the same reaction? Yes. In reduction of RCOH, first of all we used esterification reaction. Then the ester was reduced to alcohols. You remember? Yes. So this ester can be now reduced using H2 and Ni to RCH2OH plus ROH. Okay. Yes. So this is the esterification reaction. Okay. Yes. Now we told that the esterification reaction can happen with what? Acid anhydride too. That is RCOO. No, we'll write it more specifically. RCO twice O. Okay, in H plus, what can happen here? Here also esterification happen. ROCOR dash plus R dash COOH. Here we get a carboxylic acid too as a product. Instead of water, we get carboxylic acid and an ester. Now acid chloride we will take, that is ROH plus RCOCl, that is RCOOR dash plus HCl, RCOR dash plus HCl. Okay, completed. Yes. This is in pyridine medium. This happens in pyridine medium to remove this HCl. Otherwise, the reaction may reverse. That's the reason. It's written here. Why we use pyridine medium? To neutralize HCl formed during reaction. Okay, it shifts the equilibrium to the right hand side. Okay, something and all is given. Okay, perfect. Now I am taking salicylic acid. Salicylic acid is this thing, OH COOH. Into this I'm adding acid anhydride CO, and in what, H plus medium. What happens here? Here what, for sure OH will be converted to ester, if I am not wrong. Yes. So COOR dash COOR dash plus CH3COOH. Here there is COOH. This compound is called aspirin. This is very important. This aspirin is a very useful drug. Aspirin. The compound is named as acetyl salicylic acid. Aspirin is something like paracetamol that we use as a painkiller. Okay. This is an important reaction. Okay. Yes. Now till now you are telling about the bonds where O and H bonds were cleaving. Now we are talking about some reactions where CO bond cleave. Reaction with hydrogen halide. Very simple. These reactions are very simple. First reaction is Lucas test. ROH plus HX give RX plus H2O. H2O. RX plus H2O. This is called Lucas test. We also usually have anhydrous AlCl3 ZnCl2 used here. This reaction gives tertiary, secondary, primary. Tertiary give immediate turbidity. This is the same thing I am repeating second time. After haloalkane also we told the same. Now I am once again telling. In 5 to 10 minutes turbidity. Here it's a no turbidity in room temperature. No turbidity in room temperature. Okay, important. This is the important test to distinguish primary, secondary and tertiary alcohols. Okay. Over. Now another reaction is ROH plus PX3. The same reaction we wrote in haloalkane, haloarene 2. That was RX plus H3PO3 and ROH, not ROH, especially we used ROH, ROH plus PCl5, we get POCl3 plus RX, RX, that is RCl plus HCl. Remember this reaction. These both reaction also we use alcohol as a starting product. Here RO bond is cleaved, that way we are telling it here. Now next reaction is important, that is dehydration reaction. Dehydration, that is CH3 CHOH CH3. Take this compound, or don't take this compound, take any compound. Why should we take it specifically? We take random compound, that is COH H. Okay, H plus and heat. What happens? We get a double bond formation, that is this falls here and these two leaves as what? H2O. These two leaves as H2O. Okay, very simple. Usually this method is used for preparation of ethene. The same method, that is H2SO4 423 Kelvin, for 43 Kelvin. This method is used as a preparation method for preparation of ethene. Ethene, very important reaction that we learned in hydrocarbon, preparation of ethene. That is the dehydration reaction is undergoing there. This is the preparation of ethene. Okay. But the thing is that primary alcohol only undergo dehydration in normal condition. Secondary and tertiary will undergo dehydration. Secondary and tertiary need special or milder conditions. That is the acidic content should be less, or some conditions are different. That is for secondary alcohol to undergo dehydration reaction. There this reaction has its presence. We use 85% H3PO4 solution, not H2SO4. We use 85% H3PO4, phosphorus acid, okay, orthophosphoric acid, something like that, and we get the dehydrated product accordingly. Important. For tertiary, we need somewhat other condition, more milder, if I am not wrong, more milder condition. That is, take this compound. Here we need 20% H3PO4 only. That is very mild condition. And somewhat less temperature. Here we need 443. Here we need 440. Here we need only 358. So milder conditions. Here the product we get accordingly what? C double bond CH3 something like this as the plus H2O as the product. Okay. So dehydration of alcohol has some order. Milder condition means fast reactions, like in small temperature itself if the reaction is initiating. Tertiary, secondary, primary is the reactivity towards dehydration. Look, at very less temperature is the tertiary alcohols undergo dehydration, but primary needed high temperature, secondary also needed comparatively high temperature than tertiary. So the order is tertiary, secondary, primary. Okay, yes. Then the mechanism is given, and let us skip the mechanism for now. Okay. Now next one is oxidation reaction. Oxidation reaction, that is we are having HCOH bond, and this will be converted to C double bond O. This is oxidation reaction. This oxidation reaction is what we are doing for the preparation of what? Carboxylic acid, aldehyde, ketone, etc. So next chapter also we learned the same. So what is happening here is that we are taking an alcohol, CH2OH, oxidation happen. What we get? We get a CHO. We get an aldehyde. Now if we once again oxidate or oxidation happen, we get carboxylic acid. Yes. So if we need to convert alcohol directly into acid without this aldehyde step, directly into RCOOH, we can use strong oxidizing agent like alcoholic KOH or what? Acidified potassium permanganate, that is acidified potassium KMnO4, etc. Strong oxidizing agents can be used. But if we want to stop the reaction in aldehyde, that if we want to get aldehyde from alcohol, we usually use anhydrous CrO3 for getting aldehyde as a product. Or the anhydrous CrO3 has a problem that if the compound is something like this, CH3 CH double bond CH single bond CH3 CH2 CH2OH. The compound was something like this. The problem is that if you use CrO3, this bond will be what? This bond also will be what? This bond also will be oxidized or reduced accordingly. That should not happen. The isolated double bond should not be affected. So for that, there is another reagent that we can be used, that is RCH2OH. To convert it into aldehyde, we can use PCC, pyridinium chlorochromate can be used for converting the same. This is RCHO. We can make it as RCHO. That if there's a double bond, that is, take this reaction, CH3 CH double bond CH2OH. If you use PCC, the double bond don't have any problem. The double bond won't be affected. Only the OH group will be converted to the corresponding aldehyde group. Okay, noted. Yes. Now we are having a secondary alcohol. If you are having a secondary alcohol, till now you are telling about primary alcohol. If you are secondary alcohol and if you are using anhydrous CrO3, what happens here is that here also the same reaction we have shown. That what happens here, look, CHO will become C double bond O. So here also the COH will become RC double bond O R dash. Here we get ketone, not aldehyde, a ketone as the product. So primary alcohol gives what? Primary alcohol gives us primary alcohol gives us aldehyde, secondary alcohol gives us ketone, tertiary alcohol do not undergo oxidation reaction. Now the same oxidation reaction can be undergone with another method, that is, take a alcohol and at a very high temperature use a copper gouache on the surface of copper and pour the alcohol. What happens is that there the oxidation reaction take place and we get RCHO. If it was a secondary alcohol, this COH plus R dash, Cu at 573 Kelvin. What happened? We get R C double bond O R dash. We get ketone. But I want to ask you, if it was just we are taking a condition that C H R dash, it is a tertiary R double dash R dash, tertiary alcohol Cu 573 Kelvin. What happened? Here this hydrogen will be eliminated and a double bond will be formed. It's very important. They can ask you, a double bond will be formed accordingly as per whatever rule, say it's a rule or say it's a rule, the double bond will be formed. Okay. Yes. So this is the thing for tertiary alcohols. Tertiary alcohols. So this is the case of tertiary alcohols. Now we have electrophilic aromatic substitution reaction. Oh, what is it? Before that, next we have the next set of reaction, that is reaction of phenols. What are the different reaction of phenols? One, electrophilic aromatic substitution. Just electrophilic substitution. Okay. Look, phenol is an orthopara directing group. Resonance is there. I told you it is same as the haloalkane halorine condition, that look, double bond here, this will be falling here minus. So here minus charge can come, here minus charge can come, here minus charge can come, at 3 position minus charge can come. So electrophilic substitution is possible. So into phenol, if I am adding HNO3, dilute HNO3, what will I get? I will get para nitrophenol or ortho nitrophenol. This is para nitrophenol, the other, this is ortho nitrophenol. Okay. Here this ortho nitrophenol and para nitrophenol have some speciality. Okay, that we should talk. The speciality is that ortho nitrophenol have intramolecular hydrogen bonding, intramolecular H bonding, whereas para nitrophenol have intermolecular hydrogen bonding. Don't forget. So the ortho and para isomer can be separated by which method? Steam distillation, due to their different boiling point. Distillation. Which one has more boiling point? Look, intermolecular hydrogen bonding means its boiling point is more. Intramolecular hydrogen bonding means its boiling point is less. Intra means the compound is associated with themselves, so no problem. Inter means compound associated with the other molecules, so more strong molecular forces there, so the liquid will not easily separate and go away. But intra means the thing is that inside one molecule itself only there is interactions, it's not interested with the other molecules of the same compound, so their boiling point is what? Less. Okay. So this is in the case when we use dilute nitric acid. Instead of dilute nitric acid, I am taking phenol and adding concentrated nitric acid. My God, what happens? We get 2,4,6 trinitrophenol, or the same have a special name, very important name, a very important common name, that is picric acid. We get picric acid. Very important. Very important. We have picric acid. Nowadays picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts it to phenol 2,4-disulfonic acid, such a thing is written after giving this compound in a NCERT textbook. This thing is very important. Nowadays, picric acid is prepared by treating phenol first with concentrated sulfuric acid. This is nowadays. Look, now we are living in the present. So nowadays thing is very, very important. This thing is important. Last time annual for JEE means the reaction is not there in your textbook. They have only asked something with a question mark. We have to find the reaction. But this reaction is important. Okay. First, take phenol and treat it with. So nowadays what we do is that we'll take this phenol and into this we add first of all concentrated sulfuric acid. So what we get a compound that is orthopara, just orthopara. It is not 2,4,6, it is just 2,4 substituted. 2,4 substituted. The name of the compound is SO3H. Only no, it's not there here. Nothing is there. So only 2,4 substituted. The name of the compound is phenol 2,4-disulfonic acid. 2,4-disulfonic. Just 2,4-disulfonic acid. That's very important. 2,4-disulfonic acid. This thing is taken and reacted with the concentrated nitric acid. They are doing the same for purity. For purity, nitric acid we get what? 2,4,6-trinitrophenol or picric acid Picric acid. This is the thing. Picric acid. Yes. So we get picric acid. Are you okay with it? Yes. So this is the process that we use nowadays. Nowadays we use this process. Okay. Now bromination or halogenation. Take phenol. Now halogenation, the reaction name. Halogenation. We are taking the phenol. And into phenol we are adding bromine in CS2 medium. If we are adding bromine in carbon disulfide, limited addition happened. Limited once again electrophilic substitution. Limited substitution happened. That only substitution in ortho or para portion happened. Okay, ortho or para portion happened. 273 Kelvin. Okay, here what happened? We get orthobromophenol or what? Parabromophenol, depending. Para will be the major product, less steric hindrance. I told you. Always para will be the major product and ortho will be the minor product. Okay, let it be like that. The usual halogenation of benzene take place the presence of a Lewis acid such as FeBr3, which polarizes the halogen molecule. In case of phenol, polarization of the bromine molecule takes even in the absence of Lewis acid. Why no Lewis acid is used here. Usually in halogenation we should use some AlCl3 or FeCl3 etc. In haloarenes and all we use, but here we don't use it because the reason is that highly activating power or effect of OH phenol group, not OH group, phenol group. Okay, yes. Now I am taking the phenol and I want to add bromine at all ortho and para position. Thing is that just pour some bromine water into it. Just treat it with the bromine water without CS2. This carbon disulfide will slow down the reaction and control the reaction. But when carbon disulfide is not there, no control. So it's uncontrollable and we get 2,4,6-tribromophenol. It's important. These reactions are important. 2,4,6-tribromophenol. Okay. Yes, tribromophene. Okay. So these are about electrophilic substitution reaction. Now next are some important named reaction, that is Kolb's reaction. Kolb's reaction. That is, take alcohol, take phenol. Into phenol add carbon dioxide. Into phenol add NaOH. Kolb's reaction is preparing what? Salicylic acid. Kolb's reaction is used for preparation of salicylic acid. NaOH we are adding, so we get phenoxide, that is ONA, phenoxide, sodium phenoxide. Into sodium phenoxide I am adding carbon dioxide, then I am hydrolyzing water. What happens? Water or H plus, anything is preferred, water or H plus, anything. Okay, I will write H plus. Okay, so what happens is that we get OH COOH. This is called salicylic acid. This is called Kolb's reaction, not electrolysis. Kolb's reaction. Now next reaction, one of the most important reaction, that is Reamer-Tiemann reaction. Reamer-Tiemann reaction. This is the reaction for preparation of salicylaldehyde. Instead of the COH group, CHO group will come. Salicylaldehyde. Here there is a intermediate form. That is the reason why this reaction is more important than Kolb's reaction. So we are having OH. Now we are adding NaOH and CHCl3, that is chloroform. What we get here? We get an intermediate, that is ONA, that is O minus Na plus and CHCl2. This is an intermediate. If we need, we can separate this stuff. This is an intermediate. Got it. Into this, once again I am adding NaOH. So what I get is, it is O minus Na plus, and this thing will be converted to aldehyde. Now into this I am adding H plus, so this H will go and join here, and hence we get the needed compound salicylaldehyde. Okay. Over. This is Reamer-Tiemann reaction. Next reaction with zinc dust. This reaction is also an important reaction. You can just learn this. Take phenol, add zinc dust, we get benzene and ZNO, not ZNOH, ZNO. We get benzene. This reaction is the reaction used for preparation of benzene too. Now next one, fifth one is oxidation reaction. Very simple. It's a very common compound we are getting. This compound, please by heart it. Add the needed reducing agent, that is we are using NaCr2O7 instead of K2Cr2O7 and H2SO4. We get benzoquinone. This compound is very nice to see. This is the compound. This compound's name is benzoquinone. Okay, just learn. So these reactions just learn. Reamer-Tiemann reaction is important. Kolb's reaction is also important. Okay. Yes. And that Br2 and Br2 in CS2 medium, Br2 in normal medium, phenol 1,2 disulfonic acid, that thing and all is very, very important. Learn it. So by this we are coming to an end. Yes. So by this we are coming to the end of alcohols and phenols. Now we have the next set, that is ethers. So we will be doing ethers in the next video, because now itself it is 1 hour 14 minutes. So we will be doing ethers in the next video. Thank you.